So moving to the question number one, regarding this section B, that is the word design section, in which we are going to cover the strength of material and machine design. The question type, like 1 mark question were two questions, and the total number of questions for 2 marks were four. So totally, how many questions were asked? Six questions. And what was the weightage? 10 marks, right? Now moving to the question number one, as you can see, what they are asking, which one of the following is the which one of the following is the definition of the ultimate tensile strength obtained from a stress strain test on a metal specimen, right? The first option what they have given is stress value where the stress strain curve transition from basically the transitions from elastic to plastic behavior, the maximum load attained divided by original cross sectional area. C option, they have given the maximum load attained but divided by corresponding instantaneous cross sectional area, and D option is stress where the specimen fractures. So before answering this question, we will draw the stress versus strain diagram. So if I plot it, the diagram, like if I take any example of low carbon steel, mild steel, then we have the linear portion, then transition from elastic to plastic, then it is like this. Whereas this is the graph which I have drawn with the red color, that is the engineering stress versus strain diagram. Now whatever the graph I'm drawing here, that is something what? This is the graph regarding true stress strain curve. And the red color which I have drawn, this is something what? Engineering. This is stress versus strain curve. Now we should know the differences between these two because it is very, very important, right? Here, whatever the plot we have drawn, engineering stress versus strain diagram, we have plotted by taking original cross-sectional areas, by considering original cross-sectional area. By taking the original cross-sectional area, we have calculated each and every point, whatever the stress value and whatever the strain value. Through stress versus strain diagram, we have drawn that particular plot by considering the instantaneous area. Instantaneous area. Coming to the point, if I mark the point, like we have the A point, then we have the B point, then C, D, and then we have the point E, for example, then point F. Whatever the point E is there, the point E is corresponding to ultimate stress. What is this? Ultimate stress. Whatever the point E is there, that is corresponding to ultimate strength, ultimate stress. And how we are getting the stress value? How we are going to get the values of stress there? The value of ultimate tensile strength, sigma E, we are going to get P max divided by original cross-sectional area. You can see at a point E, we are having the maximum stress among all the engineering stress versus strain diagram out of 0, A, B, C, D, E, F point. E point, we are going to have what? Maximum amount of stress. That means maximum amount of load we have applied. So what we can call here, how much of maximum amount of load we are applying. And if I take the ratio of this maximum load to the cross-sectional original cross-sectional area, I'm going to get what? Stress at a point E. That stress at a point E is nothing but ultimate stress, or we can say ultimate strength, right? So if you look at the option, what they have given, the maximum load attained divided by original cross-sectional area. That is option B. Because in the universal testing machine, you are going to get this particular engineering stress versus strain diagram, right? So in that particular case, whatever the point is there, that will be showing you ultimate tensile strength. Because on the true stress versus strain diagram, you are not going to get the ultimate tensile strength because it is taking considering the instantaneous cross-sectional area. So it is a quite variable, right? In the true stress versus strain diagram, whatever the maximum value of the stress will be there in the true stress versus strain diagram, that is quite high as compared to the maximum stress we are getting in engineering stress versus strain curve, right? So whatever the plot we are getting from universal testing machine, that is nothing but engineering stress versus strain curve. And from that, we are going to get the out of all the points, what is the maximum point of loading? E point. Now you might be thinking, sir, what is the F then? F is nothing but the fracture point. This is nothing but fracture point. Corresponding to whatever the stress will be there, that is nothing but fracture stress, or we say rupture strength or fracture strength, right? So this is a very, very important. At the point E, what is happening? The necking will be started taking place. The necking will be started taking place, right? So that is the significance of point E. So what should be the correct option? B should be correct, right? D is not correct. The specimen where exactly it is failed at which particular stress, that is a fracture stress. That is not the ultimate tensile strength, right? And the stress value where the stress strain curve takes the transition from elastic to plastic, that is also not the ultimate, because whatever the transition is taking place, that is taking place from a point B, right? Because till point B we have elastic range. Here we have the elastic range, and from here whatever the range we have, that is a plastic range. That is the plastic range is started taking place. So transition will be taking place at a point B. Point B is not a maximum stress value, not a maximum loading value, right? Now try to see the question number 2. What they are asking, a structural member, which is subjected to loading condition has a uniform state of a plane stress, which is usually given the notation sigma x, sigma y, and tau xy. The yield strength of the material is 350 megapascal. Yield strength means they have given sigma yt. In the problem, if they will be mentioning like yield strength in SARE, then only we can write tau yield. If it is not mentioned like that, that means what? Sigma yt it is given. If the member is designed using the maximum distortion energy theory, what is the value of P at which the yielding will be started taking place? Right. So for solving this question, what are all the data we have given? Sigma x. What is the sigma x value? Sigma x value they have given as 3p. Sigma y is minus 2p. Tau xy is root 2p. The yield strength they have given as 350 megapascal. Now, we know that the value of when we are trying to calculate the equivalent stress, that is a sigma yt divided by factor of safety. If that is equal to yield strength, you know, when this equivalent stress that is equal to yield strength, then we say that the failure of the material will be started taking place. But how to calculate the equivalent stress or von Mises stress? We know the formulas, right? A very general formula for 3D loading case. If I'm going to write for the 3D loading case, so this is what the formula we have. So let me complete this one. This is the whole bracket. Half is a basically we have taken the here. Yeah. Then we have plus 6 plus tau zx square under root of that. So now if you just see in the problem, sigma z it is not given, it is 0. Tau yz it is 0. Tau zx it is 0. So we can just cancel the sigma z is equal to 0, sigma z is 0, tau yz is 0, tau zx is 0. So what is the equivalent stress, which is nothing but sigma yt divided by factor of safety? What we can write, guys? Under root of sigma x minus sigma y whole square plus sigma y square plus sigma x square plus 6 tau xy square. What is the sigma equivalent, guys? Again, if you try to open the bracket, then what you can get, guys, here? Yeah, sigma x square plus sigma y square minus 2 sigma x sigma y plus sigma y square plus sigma x square plus 6 tau xy square whole divided by 2. Because 1 by 2 we have already taken a common, right? So if you just solve it, what you're going to get, sigma equivalent sigma x square plus sigma y square minus sigma x sigma y. We can see that here plus 3 tau xy square. For 2D loading case, you can remember this particular formula. You can remember this particular equivalent von Mises stress. Now, if I try to equate this sigma x is what, guys? 3p square. Sigma y is minus 2p square. Again, minus sigma x sigma y. What is the sigma x, guys? 3p. Sigma y is minus 2p plus 3 tau xy. 3xy, what is the tau xy? Root 2p. That we are taking under root of that, and that we are equating to what? Sigma yt. What is the sigma yt? 350. What is the factor of safety? 1. So if we try to calculate here 9p square plus 4p square plus 6p square plus 6p square. So what you're going to get, guys? You're going to get 5p, that is equal to 350, where p you're going to get 70 megapascal. 70, sorry, what is the value of p here? 70 megapascal. That should be the answer. So if you look at the option, A option is correct. Now moving on to the next question here. Now read the problem here, guys. Here we have again the question from the strength of material. A linear elastic structure under the plane stress conditions is subjected to two sets of loading 1 and 2. The resulting state of stress at a point corresponding to these two loading are shown in the figure. If these two sets of the loading are applied simultaneously, then the net normal component of stress will be what? Right. So I'm just drawing the component A. For this one, what is the loading? The loading is given as sigma. So obviously for this one, sigma xx will be plus sigma. But what about the second scenario? The second scenario, they have tilted this element by the angle 45 degree. If you look at the option, yeah. So this is a particular direction they have given. This is the orientation they have given in the y1 and in the x1 directions. Right, guys? This is the loading number 2. For this loading, they are asking what is the sigma x in this direction. What is the sigma x? Now, this orientation also they have given 45 degree. This angle they have given 45 degree. Now, there are two methods. One is a analytical method. Second is Mohr circle method. I will be explaining by both the methods. Try to understand. First, I'm explaining by I'm just taking the loading 2 and I'm just explaining configuration 2 and I'm explaining by Mohr circle method. Corresponding to this, try to draw this Mohr circle. So, what is the Mohr circle here? We have to take 2 points. A point is corresponding to this one, this plane, and B point is corresponding to this one. Corresponding to A, there is a no stress, either normal or shear. Corresponding to B, there is a sigma and there is a zero value of shear stress. So if I draw it is a uniaxial state of a stress condition, which is going to be something like this. And corresponding to here, if you see here, what you can get is here. Let me draw it. Okay. What is the radius of the Mohr circle? It's a very simple. What is the point number A? Point number A is here. What is the point number B? Point number B is here. And every radial line is a plane. Every radial line is a plane. So this is what we have the reference plane. From this reference plane, each and every angle will be measured. Each and every angle will be measured. Now, what they have mentioned, guys, look at very carefully. They are saying corresponding to this particular corresponding to this particular plane, this plane is oriented at which particular angle, guys? If you see, now what is this angle? It's a 45 degree clockwise. Because corresponding to this plane, what is the axis? This is the axis X. So now this is the reference plane A. From the reference plane A, at which particular degree this plane is oriented? This plane I'm calling what? Let's say the plane C. Plane C. The plane C is oriented at an angle what? 45 degree clockwise. Now try to rotate 45 degree clockwise. So you are going to get what? 45 degree from the reference plane. If you try to see, this is the let's say center of the circle. Let me call this to be plane D, for example, and this is the center of the circle. The center of the circle is what, guys? Sigma x plus sigma y by 2, comma 0. But here they have given sigma x1, sigma y1. So I'm writing about sigma x1, sigma y1. So what is the Mohr circle center? It will be sigma by 2, comma 0. So definitely, what is the radius now? Radius will also be, the radius will also be sigma by 2, which is nothing but tom x, which is nothing but tom x. Now, guys, corresponding to 45 degree from the reference plane, what we need to do, we need to tilt by 45 degree clockwise, right? So this is in the Mohr circle, it will be 90 degree. So this is my plane. This is my plane. What? Plane D. And what is the my different value of normal stress? Sigma by 2. And right. And what is the value of the shear stress? That is also sigma by 2. That is also sigma by 2. So what is the value? What is the value of the normal stress at XX? So corresponding to this loading, what is the sigma x for the second loading, it is sigma by 2, because the first coordinate will be what? Sigma normal, and this is a shear stress on that particular plane. So what is the normal stress on that particular D plane? And corresponding to the axis which is passing through that plane is x. So what is the sigma xx for the loading for the configuration 2 will be sigma by 2. Then what is the net stress in xx direction? Sigma plus sigma by 2, which is nothing but 3 sigma by 2. Right. So this is the Mohr-Circle method, guys. You can also get the same answer for the configuration 2 by analytical method. By analytical method. Now understand. From the vertical, from the particular, my dear friend, here you try to understand this thing. This is x, and what we have, guys, here, this is y1, this is x1. Now, from the particular, how much of angle it is making by the axis x with respect to x1, guys? How much of angle it is making? It is making an angle what? 45-degree clockwise. 45-degree clockwise. And if we take our references, we have taken in the class, theta when it is anti-clockwise, it is positive. Any plane, if you take, just for the reason, I am just writing here. Any plane, if you take, any plane, if you take from the vertical, that should be theta anti-clockwise, or axis passing perpendicular to the plane must be what, guys? Must be at an angle theta anti-clockwise from the horizontal axis. Similarly, here also from the horizontal axis, this axis which is passing perpendicular to this particular plane is making how much of angle, guys? Theta clockwise. How much of angle? 45 degree. What is the value here? Sigma x1. How much of value here? Sigma x1. What is the sigma x1? 0. Sigma y1. What is the sigma y1, guys? It's a sigma. It's a sigma. 0 minus sigma by 2. What is the cos 90 degree? Minus 90 degree, again 0. Tau x1 y1, it is 0. So what you can get, guys? Once again, sigma by 2, which is also equal to sigma xx. So again, if you try to calculate the net stress in the xx direction, it is sigma plus sigma by 2, which is nothing but 3 sigma by 2. So either by Mohr-Circle or by the analytical method, your answer must be same, right? Moving on to the next problem, guys. Try to see this particular problem. Try to see this particular problem again from the strength of material. A shaft which is having a length L is made up of two material, one in the inner core and other in the outer rim. The two are perfectly joined together and there is no slipping at the interface along the entire length of the shaft. The diameter of the inner core is di and external diameter of the rim is what, guys? D naught, right? The modulus of rigidity of the core and the rim materials are Gi and G naught. That means both are different material. It is given that D naught is equal to what? 2 times of Di and Gi is equal to what, guys? 3 times of G naught. The shaft is twisted by the application of a torque along the shaft axis. The maximum shear stress developed in the outer rim and the inner core turn out to be tau naught and tau I respectively. All the deformations are within the elastic range and the stress strain relationship are the linear. Then what is the ratio of Ti by T naught is equal to what, right? So this is the figure they have given, and why the most of the students got fear during the examination? Because of the figure. They have not given the front figure, they have given the side figure of that. That means cross section figure. If I draw the front figure, it seems like to be very easy, very simplified case as usually discussed in each and every classes, right? This is the composite shaft, the shaft in a parallel combinations. There are two material, 1 and 2. Both are bonded together perfectly and it is being twisted by the torque, torque T. Here, if I just draw here a reaction torque, it will be like this, right? The inner diameter, what they have given, guys, it's a di, and outer diameter they have given what, guys? D naught. D naught is 2 times of di. The shafts are in what? Parallel combinations. The shafts are in parallel combination. Wherever the shafts are in parallel combinations, wherever the shafts are in the parallel combinations, what will happen, guys? Angle of twist will be same. They cannot be twisted with the different angles. Otherwise, the bond will be break. They will be no longer will be called as composite shaft or shaft in a parallel combinations. Now, what is the shaft one? The shaft one is basically what, guys? You can see that there's a two shaft, but what is the inner core material? Inner core material is Gi, which is nothing but 3 times of Z naught, right? Now, understand what is the theta one. Theta one, what is the material one? Material one behave like a what? Solid shaft. And material two, whatever the shaft two is there, it will behave like a hollow shaft, right? So, what is the shaft number one? It is like a solid shaft, and the shaft 2 is nothing but what, guys? It's a hollow shaft, right? For the solid shaft, what is the theta 1? What should be the values of, see, what is the T? T must be equal to T1 plus T2. Both will try to resist this particular torque which we have applied externally. Now, what is the value of theta 1? T1 into the length of the shaft. Length of the shaft, both the shaft is what, guys? Same. T1 into L divided by what, guys? G1 or Gi divided by what, guys? J1. T2 into L divided by what? G2, J2, G2, G2, guys. Now, what is the T1 into L? What is the G1, guys? Here, L will be cancelling out, so I'm not writing here. So, what is the G1? Let's take it as G1 only. What is the J1, guys? The polar moment of inertia, guys, for the solid shaft will be pi di to the power 4 divided by 32. Right, guys? That you need to remember. What is the T2 divided by G2 into J2? What is the G2 for the hollow shaft? For the hollow shaft, guys, it's a very simple. Pi d naught power 4 minus di power 4 divided by 32. Divided by 32, guys. Now understand what is the G1? That is equal to 3 times of Z2, right? So what we can write here, pi and pi will be cancelling out. This will also be cancelling out. So here T1 by T2, which is nothing but G1 by G2. What is the G1 by G2? It's a 3 times di to the power 4 divided by something like this. Now my different here, D naught is equal to what? 2 times of D1. So T1 by T2 will be what, guys? D naught divided by what we can write here? D naught divided by di to the power 4, which is nothing but 2 to the power 4 minus 1. So what is the T1 by T2, guys? 3 divided by 15. 3 divided by 15. Now once we got T1 by T2, what is the next particular task, guys? What we need to calculate? Shear stress. Shear stress in the shaft 1 to the what? Shear stress in the shaft 2. So now we can further take tau 1 divided by tau 2, which is nothing but 16T1 divided by pi di cube. And what is the T2, guys? T2, we also know that tau 2 is what, guys? T into R2 divided by J2, which is nothing but T2. R2 is what, guys? D naught by 2. J is what, guys? Pi D naught by 4 minus di to the power 4 divided by 32. So what we can get, guys, from here, 16T2 divided by pi D naught cube 1 minus di by D naught to the power 4. This I am writing directly over there. So what we can write here, 16T2 divided by pi D naught cube over 1 minus di by D naught to the power 4, something like this. So what is the tau 1 by tau 2, guys? 16 will be cancelling out. What we are going to get? T1 by T2. What is the T1 by T2? 3 by 15. What is the D0 by D2? It's a 3 cube. 1 upon 1 minus. What is the Di by D0? It's a very simple. They have given D0 is equal to 2 times of Di. So it is nothing but 1 upon 2 to the power 4. So 3 to the power 4, 1 by 1 upon 15 by 16. Oh, sorry, it's a no, this particular ratio, this will be, this has to be in the numerator. This has to be in the numerator, guys. Because 16t divided by pi d naught cube 1 minus di by d naught to the power 4. So 1 minus 1 upon 2 to the power 4, which is nothing but 15 divided by 16. So this will be cancelling out. What we can get, guys, from here? It's a 2 cube because d naught by di is nothing but 2. Sorry, guys, here it's 2. And here it will be 8. So it's a 3 by 2, which is nothing but tau 1 by tau 2 will be what, guys? 1.5. That means inner shaft can able to or what is the maximum stress? Maximum stress are generating in the what? Inner shaft as compared to the outer shaft, right? So what should be the correct no, what should be the answer for this question? Ti by T naught, which is nothing but tau 1 by tau 2, because 1 and 2 if I take, then it should be 1.5, right? So now moving on to the next question here. Again, this question is from the strength of material. Now, this question is a little bit tricky, guys, right? But if you follow the no, BC Punmia solved example, a very similar question they have given, not exactly the same pattern question, but a part of the concept which are required to solve this particular problem already given in the BC Punmia textbook, right? And that is a very mandatory book for gate mechanical, right? If you're writing the mechanical paper, no, gate examinations, definitely you have to follow the BC Punmia. A rigid beam AD, which is having a length of 3A, which is nothing but 6 meters, is hinged at a frictionless spring joint A and is supported by the two springs as shown in the figure. The string BC passes over the two small frictionless pulleys of negligible radius. All the strings are made up of same material and having the equal cross-sectional area. The force F is equal to what, guys? 9 kilonewton is applied at a point C, and the resulting stresses in the strings are within the elastic limit. The self weight of the beam is negligible with respect to the applied load. Assuming the small deflection, what is the tension developed in the string at a point C will be what? Now, so if I draw the rough diagram, the free body diagram of here, so we have here we have the string. It's a T1, for example. Again, it's a T1. There is a load of 9 kilonewton, and again there is a string. Now, guys, why I have written T1, T2? The string which is passing through this one will gonna have the same tension. Will gonna have the same tension. T1, T1, T1. A string which is passing, no, to this one at a point D will have the different tension because it's of smooth pulley. If it is having a smooth pulley, guys, then my defend what is the tension T1 is there. Let's say here tension T2 is there. So if you take T1 by T2, which is nothing but e to the power mu theta, if it is a smoothless, frictionless pulley, then this quantity will be what, guys? Mu will be 0. E to the power 0 is what, 1. Then T1 is equal to what, guys? For example, T2 dash. T1 is equal to T2 dash. So that's why whatever the T2 dash is there, which is also equal to what? T1. If it is a smooth pulley, which is given in the problem, frictionless pulley. If there's a friction, again, machine design concept will be involved, right? Again, the length is given as AAA for all the T1 tension ropes. Whatever the ropes are here, they are having what, guys? A string, whatever the strings are here, they are having the same tension, same length A, A, A. as they have already given in the figure. You can see that the length is A. Here also length is A. Now, if I draw the free body diagram here, if I take the summation of moment about point A to be 0, see, we can take summation of moment about any point. That one thing you need to remember. We can take in a particularly space, if I given any structural member, then I can take summation of moment about any point. But why I'm taking the summation of moment about point A is because the reaction force which is offered by this hinge support will be nullified, because that moment will be 0 because of that reaction force. So it will be simplified. So what is the length here? Here we have the length A, here we have A, and then here also we have A. So T1 into A plus T1 into A, 2A plus T2 into 3A, which is equal to 9 times of 2A. A and A will be cancelling out. Then what we can get, guys? 3T1 plus 3T2, which is equal to 18. Then T1 plus T2 is what, guys? We're gonna have it like 6 kilonewton. That is the first equation, guys. But if you want to get the two unknowns, we need the two equations. What are the second equations? For this small deflection, we can tilt this particular rod or beam like this. So let's say we have the point B here, we have the point C here, we have the point D here, right? And if I draw the deflection here, this is the deflection B. And this is the point A, guys, which is hinged, guys. This is the length A. What is the relationship between the delta B, delta C, and delta D, guys? It's a very simple here. Delta B is what, guys? Delta B divided by A, which is nothing but delta C divided by 2A. So delta B into 2, which is nothing but delta C, delta D, which is nothing but 3 times of delta B. If we take the rope BC, if you take the rope BC, what is the deflection which are happening, guys? What is the total deflection in the rope which is passing like this? What is the total deflection, guys? Total deflection is, for example, delta B plus delta C, T1 into L. What is the length? A plus A plus A divided by A into E. Why we are writing here? A, A, A. You consider this as a single rope, a single string. A single string, what are the total deformations? Delta B and delta C both will be there. That is only the logic is there. That's it in this particular problem. Most of you might be understanding, maybe thinking in the examination like both are different string at the point B and C. No, they are same. Why it is same? I already explained, right? And this is the most important step. If you're not getting this step, definitely you're not able to solve this particular problem. And if you want to get this step, how we are getting in all this thing, there is a one problem solved example in BC Punmia, right? So there is a no problem in GATE examination, which is new to, basically it's like a completely new. Each and every problem is being taken from the some references. There are infinite books. I'm not saying that you follow infinite books, but you try to follow the good books which is being referred by IGC, and try to solve the at least solved example for that. If you try to solve the solved example in GATE exam, definitely you will be able to no you will be able to get the right particular trick to solve the question, and you will be getting the final answer also, and that is correct. Again, this question will look very easy, but this question is most like it is having the among all the questions from all the section, this is the most toughest question according to me, if you are not getting this particular step. But if you already know the concept, just like you know the concept of all other things, right, in the strength of material, if you know this concept also, definitely you can able to solve it. Now what is the delta B here? I'm writing delta B. Delta C is what, guys? 2 times of delta B, T1 into 3A divided by AE. So it is 3 into delta B, which is nothing but T1 into 3A divided by AE. So from here, what is the delta B, guys? Delta B, I'm going to get T1 into A divided by AE. Now, what is the delta D? Delta D, we know that what is the delta D? T2 into what is the deformation in the string which is connected at a point D, guys? T2 into A divided by A into E. I'm assuming A, E both are same. Both the quantities are same for all the strings. That is equal to delta D, which is nothing but 3 times of delta B. Delta B is what, guys? T1 into A divided by AE. So from here, what is the T2? It's a 3 times of T1. Once you got this second equation, two unknown, nobody can stop you to get the unknowns. And what is the unknown now? Here T1. What is the T2, guys? T2 is nothing but 3 times of T1, which is nothing but 6. Then what is the 4T1, which is nothing but 6. And T1 is what, guys? 6 by 4, which is nothing but 1.5 kilonewton. That is the T1. What is the T2? T2 is nothing but 4.5 kilonewton. But they are asking in the problem, what is the tension in the developed in the string at a point C will be 1.5. If they would have been asking the question like, what is the tension developed in the string at a point B, that also must be what? 1.5. So that is regarding this particular question. Now try to see the last question for this particular session here. Again, one of the very beautiful problem they have asked. Again, if you are not solving the VB Bhandari textbook which is being referred by the IGC, you cannot solve this particular problem, this problem. Because again, it is required the concept of pulley which is being attached to the shaft, and infinite number of problems are given in the VB Bhandari regarding this. Infinite number of problems. Directly, they have taken the copy paste from that particular book. I'm not saying exact figure, exact pattern, but it is almost like 95% matching the problem which is given in the Bhandari. Right? I'm not saying to refer many textbook, but whatever the textbook we are saying to refer, that definitely you have to refer. From the gate examination, directly if the question paper will be tough, they will be picking the question from there itself. Right? Now, how to solve this particular problem, guys? A shaft AC is rotating at a constant speed. It carries a thin pulley of radius r is equal to 0.4 meter at end C, which is driving a belt. The motor is coupled at the end A of the shaft such that it applies a torque mjet about the shaft axis without causing any bending moment. The shaft is mounted on a narrow frictionless bearing at A and B, where AB, BC is what, guys? 0.5 meter. The taut and the slack side tensions are in the belts are what, guys? T1 is 300 and T2 is what, 100 Newton respectively. The allowable shear stress, that means tau yield, they have given 80 megapascal. The self weights are need to be negligible. Even in some problems are given in the machine design where they have considered the weight. You have to go through that. Now again, neglecting the shock and the fatigue loading and assuming the maximum shear stress theory, what is the minimum diameter which is required, right, to sustain this much amount of loading, guys? Right. Now, let me explain this particular problem. Let me draw the first of all diagram with the bearings. There is a pulley, guys, where we have the tension T1, T2, and there is a bearings like this. Here we have bearings. Bearings gonna develop some reaction forces RA and RB. And this is the length which is 0.5 meter. I'm calling this point A, point B, and this is the point C. Again, if I draw the diagram here, if you see the pulley, because of the pulley, definitely some load will be transferred to this particular shaft. And if I draw the equivalent diagram, there is a reaction force RA, and there is a net force T1 plus T2, 300 plus 100, which is nothing but 400 Newton. Because whatever the load is there, that is being passing, transferring from the pulley to the shaft. And apart from it, it will also transmit some torque. T1, what is the torque? T1 minus T2 into R. So 300 minus 100 into point. How much of value they have given, guys? What is the value here? 0.4 meter, which is nothing but 80 Newton meter. This is the torque which is being transmitted. This is the torque which is being transmitted, guys. So how much of torque which is being transmitted? It's basically, if you see the diagram, the torque will be transmitted in the clockwise direction like this. And what is the reaction torque? The reaction torque will be what, guys? The reaction torque which is developed here, which is already given by the pulley, right? What is the torque value? 80 Newton meter, right, guys? You can see in the figure, right? So this is the torque and this is the diagram which we have drawn here, 0.5 meter, 0.5 meter. That is the loading diagram. The conversion from the component diagram to the loading diagram, which is very, very important. Now, guys, there will be some bending moment because of the load 400 Newton and because of the torsion, there is a shear stress. Both we need to calculate and then we can apply maximum shear stress theory, guys, or we also call Tresca's theory. So for that, first of all, we need to calculate reaction forces, where exactly the maximum bending moment is there. Then only we can say maximum bending stress. Then only we can calculate the maximum bending stress. So here, first of all, what is the torque diagram? The torque diagram will be here. If you see the diagram here, what should be the direction here? Here, the torque diagram will be like this. If you follow the sign convention, this is the torque diagram. It's a T and T. Everywhere torque diagram will be constant. Everywhere torque diagram will be constant, which is nothing but 80 Newton meter. Corresponding to this, what is the maximum shear stress? Or we can also say the tau. What is the value of tau? What is the value of tau here? 16 T divided by pi dq. 16 into T, what is the T, guys? 80 into 1000 divided by pi dq. Just keep it like that, or you can just calculate the values like 16 into 80 into 1000 divided by pi, which is nothing but 40743665 divided by dq. Let's keep it like that. What about the bending stress? For calculation of the bending stress, you need to again calculate the reaction forces, guys. Ra, Rb, and again there is a load of 400 Newton, 0.5, 0.5. So what is the Ra plus Rb? First of all, summation of forces in the y direction to be 0. Then Ra plus Rb is what, guys? It's a 400. Take summation of moment about point A to be 0. Rb into 0.5, this is equal to what, guys? 400 into 1. So what is the Rb? 800 Newton, which is in the upward directions. What about Ra? Minus 400 Newton in the downward direction. So what should I do, guys? I should be reversing my directions like this. Now try to calculate the bending moment at a point A will be 0, point C will be 0. What is the maximum bending moment? The maximum bending moment will be at a point B like this. What is the maximum bending moment, guys? 400 into 0.5, which is nothing but what, guys? Here 200 Newton meter. Corresponding to this, maximum bending stress will be what, guys? Maximum bending stress will be what, guys? 32 m divided by pi d cube. What is the maximum bending moment? 200 into 1000, because we are converting in Newton mm. So directly whatever the answer will be given to us will be in mm only. So if you try to calculate the bending stress, what you can get, guys? 32 into 200 into 1000 divided by pi. So you are going to get 0.2037 183.272 divided by dq, guys. Dq. Once you got this particular value, what are the maximum shear stress theory? The tau max, which is nothing but sigma bending definitely I'm not writing xy because according to a critical element, first of all you need to take the critical element, then you have to draw the state of stress. So I'm just writing tau square. This particular value of my different maximum value of this stress, that maximum value of this stress, my different, that what we need to do, we need to equate to tau yield. Tau yield. Now what we can just do, guys, we can just keep the values here 20 37183. What is the value here for tau here? 407436. 407436.65 dq whole square, which is equal to 80 megapascal. Which is equal to 80 megapascal. Which is equal to 80 megapascal. See, understand, according to maximum series stress theory, according to MSST, this tau max should be less than, actually that should be less than tau yield. That should be less than or equal to tau yield for the safety conditions, right? So correspondingly, if you try to calculate diameter, the diameter you should be getting minimum to minimum, at least it should be 23 point. You can calculate, through virtual calculator, you will be getting 23.93 mm. That should be the minimum diameter required. Otherwise, material will fail, according to Tresca's theory, right? So, what should be the correct option answer for this question, guys? 23.93 mm. Please make a note of it. So, one of the good problem. Again, I'm saying if you're not solving the textbook or if you're not solving the test series, you may not be able to attack this type of problem in the GATE examinations. These are not the regular questions which is keep on asking, which they are asking every year. No, every year they are not asking this same fashion question, but whenever they are asking, you need to be thorough with this type of concept. Directly, you cannot, in examination, everything will not be come to your mind. Right? So that is all about this particular thing, guys. Some of you might be thinking why we have not notated by like whether sigma bending is sigma xx or sigma yy. So everybody know this basic concept. See, this is the what we have z direction. So definitely, if it is a z direction, bending stress will be what? Sigma z z. Sigma z z. Along the longitudinal axis, there will be whatever the axis will be there. That will become what? Direction of the bending stress or normal stress. What about the tau? Whether it is the tau xy, yz or zx, that also must be taken care. So again, in examination, no need to worry. But as a basically, if you precisely solve each and everything, then for that you need to take the first of all critical section. The critical section will be here. This is the critical section because there you have the maximum bending moment, maximum bending stress, and maximum shear stress. In that case, also by definition, you have to take a section where you have what? Maximum shear stress. Where exactly the maximum shear stress? At a point B. At a point B, you have, suppose there is a circular shaft, then everybody know that because of the torsional, because of the torsion, there is the shear stress will be developed like this. So again, whether you are considering top A point or B point for the consideration, B dash point, accordingly you have to draw the state of stress. Suppose you are considering A point as a critical section. You are considering A as a critical section. Again, at B also you can draw like this. Suppose A point you are considering the top notch point, the top point you are considering at section B, you are considering as a critical point at a critical as a critical section. That what should be the value of tau, guys? What should I represent? I should represent it which phase? It is passing through jet phase. In which direction? Y directions. For the point A, I'm writing for the point A. So definitely whatever the values should be there here, that will be replaced by here tau max. Tau max will be replaced by here sigma z z minus sigma yy by 2 whole square plus tau yz square. Because what we are getting guys here, we are getting tau yz or zy, right? Sigma yy it is 0, sigma z is given, tau yz already we have calculated. Put the value, get the answer. So that should be the if you properly writing the exam, then you write each and everything. You have got this step you will be getting full mark. But in exam, don't do this type of research. Only try to get the answer as quickly as possible and move on to the next question. Right. Thank you all.